with as few comments as possible along the way. The first step is based on data just been accepted by physicists a week ago. There have been quite a few genetic studies recently, German group, PTS group, Hagger's and some group, etc. So what I'm talking about today, the first step is an extension of the network. Here is just extended domain. We need to calculate calculation. The top surface is temperature 0 and water temperature at 1. Quantum number is 1 because I want to trace the fluid use temperature tracer. So here is the resolution. This is the delta E plus delta x plus the solid line, less than 5, less than 6, delta x plus. And here is the all normal resolution at 4 different random numbers. As you draw a line vertically inside the boundary there, you can see all the resolution are less than 8 or 9%. So here is the goal resolution. And here is the shift factor. The grease is brightest, then the grease is intermediate, etc. distribution. Here, PWMs increases slightly with random number of grease is given, and here's the tau WMS stays pretty flat over this particular random number range. And here, according to random dynamics, because I'm using quantum number 1, so it stays and when the line region is expected, in the present region it also stays at 1, so pretty good. Here is the comparison. The mean velocity is oscillator with Raquel. And here is the temperature profile. This is a set of 3 profiles at 1410. The same random number. This is slightly different. Regarding the shear stress, Jensen did not split it over here. And here is a comparison with PTX different data. Slightly different, but they're pretty good. And this is the common number is low, so we don't have this segment repeating. So it's low and low. These are data reviewed by casing in harmless speech that I need because the manual for any people. And this is basically a comparison of thermofluxes normalized by the local intensity. So I'm going to show some for visualization. So this is the Q0 isosurface in the transitional region. This is the same region but with the isosurface temperature. Here is the temperature 0.01 when at the wall. So this is the closer to the thermal boundary at. So this is the graph in the 16. So the 400. This is the 650 also. Here is the 1300 from 10,000 to 1300. So this is the start region, 1410 region roughly. So this is the 1600, 1800, 1900. These are the isosurface temperature from 500 to 1000. They show signatures of the airplanes. So this is the downstream region to 1700. This is the end of the relation domain. So this is just a simple view of the steam friction. So pretty well with the glasses right from the beginning and we have two spots here and after transition. So the short summary from this first set of slides is that it's quantum number set water in and how the MS black and white space black almost independent with RT that is distribution and have a lot of terpenes. It's similar one that seems to be quite useful in coherent structure detection.
Can I ask you?
Yes.
Point number 2. Then, what was the value of this tau?
0.44.
0.44.
Yeah.
Can I ask you?
Yes,
near the wall, carbon quantum number is about 2 in your case.
1.9, yeah. 1.9.
Carbon quantum number?
Yes. Yeah.
Very close to the wall.
Yeah,
I think
you're close to, yeah, as you said.
Yeah, very close to the wall.
Yeah.
Your value, I think 2.
Yeah.
Right?
Yeah.
But
1.9.
I think that there is a very minimum value, the 1.1 near the wall, obtained by channel simulation.
Yeah,
and also the VHR.
Yeah.
So the
Can
you say?
Yeah, we can debate about that.
Okay.
That's the whole point. The whole point of case requirement speech.
Yeah.
see the title, if you read the new paper, his title is Trivial Quantum Number, Where Are We the Tensor? And there he made a big point why in attitude is double peak and physics from the better ratios this
Anyway.
Okay, yeah, very
Is there any physics? Is there any physical reason for the Taban quantum number? Is there any physical reason? I think the value 2 meaning the departure from the singularity, I think, between the velocity and the scalar field. So can you give us any comments on?
Yeah, no. Yeah. Let me run through slides and
okay.
So now I'll move on to the second set of slides. Also, I want to do this very quickly. So again, this is an extension of the Superman work. So here we make 2 points, sort of things, and then we also saw this two-shear overshoot shooter, which is larger than the normal overshoot stress, very close to the wall, but the normal region is to 0. Then also we saw this breakdown process, pretty capture the formation for every packet as a random set. So now the question is whether these three phenomena depend on a specific type of inflow existing disturbance. So we introduced the simulation of the broad side because we're putting this. So we just like to resolve this in simulation. Again, we have a lot of simulations. So now these are the weights. But they are pretty difficult to see, and so now I think we need to do review. So this I will do the velocity profile, I will do the temperature profile with the simulation. So here, these are the velocities, the boundary layer is the weight. And here are the thermal boundary layers, so something like that. So just not make it easier to see. So this resolution is still the same, roughly. Yeah. And then 1 plus less than this. So previously here, our profile basically largely almost exactly what was beginning here we have this bound because the weight has mean deficit, so this was the boundary layer. So again, this Taylor mass stays pretty flat, and Taylor mass increase. So here is CPW in the previous set of results with the block substitutions. This is the current CPW. So in the transitional region, the sign are different wind favorable wind factors, but in free region, the gradient is the same. So again, this means that the comparison with Clark at 1410. So this region shows the effect of the weight in the phase stream. So previous set of results here will be dropped to 0, but we will have this phase finite. Here's the overshoot we are talking about. Starting from IC to 300 to 600, 670, 1410 to 700. So there is overshoot of Wilshire stress. So these are the schemized development of the peak profiles. This is the approach we're talking about. So we'd like to know what's the possible value of this overshoot. Turns out the tau dy almost follows the trend of UDX on this local acceleration in the transitional region for the fluid spots. So that is why we have this overshoot, the change sign of overshoot trend. So now move to Gaussian studies. Pretty much you can summarize the previous experimental work starting from pattern modifying. And in the simulation, now we have this theoretical work apparent Chung, etc. And there was some numerical work more in the team by Robinson and Klein. Robinson did it himself. So these are the isotopes of the Q in the transitional region of the merged Truman spots. They're categorized by the field. So whether you have weight or have outside fluence in the increasing doesn't matter. So these are the isotopes of temperature in the same region, same instant as the previous slide, so at closer to the boundary edge. So this shows signatures. So now I just abandoned the QX look at the temperature closer to the boundary edge. They are colored by white, while the America to red means we're at boundary edge. So in the transitional region, from 400 to 800, this is from 800 to 1200. And this is 1215. So now this is 18 and 13 like this. So, some of our people, we're pretty, colleagues of Intel, we're very skeptical of how many tell they're really helping the policy, using their logic. So now the next one I have to do is I'll just take this thing and zoom it out. So this is the new view of the previous structures, but I just use different threshold. So this is, we just take a 3-timer task. This one, and we will see the details. So these are the PY services for the same region. So again, this is the thing we're looking at. This is the XY plane. We see the hat. So these are the two legs, and these are the two elements. Actually, Parviza cases is very advanced because these are open to invitations. But I agree with him in the sense that if we only have this without the previous stuff, then you can interpret this in many different ways. But that is now with the isothermal temperature, the Q-surface isothermal, and these instantaneous straight lines. They do improve it shows that they are really similar. So from here we can tell actually there are variables. So now the next question is this, which is a very important one, is whether we have new hairpin vortices in the terminal region being generated at the wall. So that is a pretty important question how to address whether the hairpin vortices we saw previously, those are at the boundary X, they're colored red. So now what we do is, so this is at this particular instance, these are the thermal boundary layer. Again, so now at 47, I set the outscaler to 0. So then we have a final temperature at the wall. So then slightly later, 46.2, now we have the regeneration of the young thermal boundary layer. So this is, but without any change of the velocity. So it's just velocity will develop on its own. So this older thermal boundary layer, so the science at 0, so now we have the young thermal boundary layer. So we'd like to see whether we have a new hairpins being generated here. The reason for this to reset this thing to 0 is because the outer edge of the boundary layer carries, in my view, more easily visible signatures of hairpins. So that's what I do. So this is at 47. So this is something like just 47.1. Now we have this bunch of stuff. This is slightly later. They become red. The red here means 15% of the boundary layer thickness, and yellow means 7%. Translated to word units about here 0.1 means 60, y equals 60 volts. So this is slightly downstream, around 1800. So I have to zoom on this particular structure, see what's really going on here. So again, I take 3 camera cuts. So again, here, this is why I do this in here. So my son Edison is 5 years old. He just had his birthday. So later, if I put his t-shirts he has been wearing since his birth, then this is what I see. But this I cannot find Edison here. Edison is actually here. So this is the hairpin. This is the hairpin responsible for all of the t-shirts. So that's it. So that is when you see this bunch of stuff here. But no, again, if everyone has a sibling, then sibling might be sitting here. Then we have to impact this. So then this is the head. These are the legs. These are the tail. So this is the 47.2 side later. You see that previous stuff becomes red. More half this guy. So again, this elements that. We have the case system. So I think I'll stop here, yeah. Because the next is where do these plots come from? This is the same as what our new assignment model is about. Thank you very much.
For a very long time, I have maintained that hairpin is a legacy of transition. And if you run this simulation long enough, it's very hard, of course, to you will not get preponderance of hairpins.
Yeah, yes. That's what
So there is no reason why hairpin to survive. They do form the lambda-type vortices with transition, and you just have to wait long enough for them to decay.
Right, right, yeah. Now suppose as physics if you go to that, I see that 8,000 or so, then maybe there are few less. I just said, but I should add a qualifier. My study is limited to 1800. I see.
So that we
beyond that,
agree.
yeah, beyond that, I don't know. Slight difference.
Can you please go back a couple of slides?
Yeah.
One of your analyses has been you have these in a correlation with your how much are those in 3 points?
Oh, in grid points, let me think here. This thing, I have 8,000 points to this, from 0 to here, 8,000. So if I divide this guy by 10, so every 1,000 of this thing, I have 800 points. Every 1,000, I have 800. Then every 400, I have. No. Every 1,000, I have 800. 1,800. Then 400 this kind of thing would be 300 points also. 300 from here to here.
Just trying to get a feeling of how thick are those, these
Right, yeah. So from this guy to this, the thickness is about
In X problem of 10.
So the boundary thickness is 200 here. It's 200 there. So from here to here is 1 there.
Yes, so how many are there in this case?
So therefore, this 1500 of percent of 200 would be 30. So
Yeah, those are the slices.
are you sure that those are not 3 points or 3
Yeah, I think those are great points.
yeah, well, there are 300 points from here to here, 400 points from here.
I don't know which one first, but
What I really would like the two of you to answer is a question that we've been aware of in the experiment for years. It's very hard to find a unique zero pressure gradient boundary layer at Reynolds numbers 2,000, 3,000, 4,000. In fact, if you take a look at some of the early attempts to modify turbulent boundary layers to get drag reduction, you can have the same Reynolds number, the same RE theta, the same RE delta star, and in many different ways the boundary layer is not the same. We can also make those changes in the laboratory by the tripping process. By the way, you get to the, this is so well known in many different ways. What I think would be instructive to us, and as both of you know, I've talked to you individually about this, it would be good to take two data sets like this and actually compare them at few Reynolds numbers that are comparable, maybe like 1,400, 1,400, 1,600, or something like that, and see how different, and do some statistics on hairpins or whatever you agree on as an objective measure to tell us, because that would educate us in terms of what are the best ways to generate the numerical turbulent boundary. And I assume, also Javier in this, because you are, so all the 3 or 4, Philippe, I don't think you actually did this, if I understood what you presented. You did a lot of the average statistics, but I'm suggesting to do sampling of the characteristics. I don't think you did.
No, but that's a work in progress.
Yeah, I think it should be of all the data sets we have and tie it into how the transition was done.
I just had a clarifying question. In all of your simulations, you have these passing waves. You're generating the turbulence by the passing of these waves.
Right.
Is that correct in all of these simulations?
No, I presented 2 sets of slides. The first set of slides are from a result with isotropic principle blocks. The second set of results are with the Higgs.
Okay, so in one case it's the blocks going past, and the other ones it's the waves.
Yes.
So you're generating the turbulence by some really big blob of turbulence in the wave or something going
Right.
about. So I mean, in my mind, this is completely different. But this has nothing to do with an equilibrium turbulent alternator. So you know, why should it be exactly the same?
Right. Now, see, in the first case, you guys have two clocks. They are pretty weak, and independent level pretty weak. And if you look at the RMS value outside boundary, they're getting a very small level. 0.5%.
Yeah, but I'm sure that if you calculate the Hubbard question about the differences in how you trigger turbulence, you know, you're not usually in the experiments triggering it by this really large things coming on. You're doing something at the wall very close to the leading edge, and still you can get quite different evolutions, as you were saying, Hassan. So if you do something like this, which is huge difference, of course there's not, you know, I mean, why would you expect something exactly the same?
I agree with you from the This weak thing is purely, we did it purely for to answer the question in regards of the inflow with respect to the phenomenon. I think the first set of results with intermittent absorption plot, they are much closer to the canonical boundary layer in terms of statistical measures you can see. And so this weak thing is its impact on boundary is pretty large. But that's the point. With a very large impact on boundary, you want to see whether we still have this kind of hair. We'll see what as we saw before.
Even in experiments, the different people use different trips. So the transitional part, especially the near wall, it could be autonomous. So it can develop its own innate turbulent boundary structure. But the outer part will very much depend on the type of trip you use. And most people use trip without really understanding what trip to use. Sandpaper and a cylinder and a span-wise corrugation or teeth, they will all produce different structures.
Back to Hassan's point, Ardita are working on something further with this, so we're trying to address the issue with a more canonical
very fast.
Comment, and it relates to the discussion. I think, the thing about comparing different simulations is like comparing instantaneous realizations in any experiment. You're never going to see the same thing twice. And what would be more valuable is to actually see if you can extract some sort of average, statistical structures rather than instantaneous realizations. I mean, when we talked about hairpins, you put that into a statistical model, you're never going to see a perfect arch. But the average, it must be, otherwise you've got a cross plot. Okay? So, these sort of, but that sort of information would be very valuable. That sort of statistical information. It doesn't, you don't have to, like if an average person is half male, half female, or 51, 49, and you're never going to see that. That's a valuable concept.
Caleb is doing that. Right now, extracting using the structures statistically.
I think we should stop the dinner. So thank you to everybody for